Hi guys, welcome back to 7 Steps to a 7 in Olympiad Geometry. In the last video, we looked at lengths and special theorems involving them, such as the law of sines, the Cheva's theorem, and Menelaus' theorem. And the main efforts in the last video were to prove things involving the law of sines and using the law of sines repeatedly. In this video, however, we're going to be stepping away from the law of sines and explore a much more distant concept known as homothety. All right, so what exactly is a homothety? Well, before we get into that, let's provide some brief motivation. So remember how a few videos ago we were looking at two circles here? And let's consider if we construct their external tangents. And they meet at this point x here. So we have these two circles and their external tangents intersect at x. So now let's take a look at this diagram, but instead from the perspective of point x. Imagine that you are standing on point x here. So this could be you. And you are seeing each of these circles. What do you see exactly? Well, if you take a closer look, you end up only seeing this circle and none of this circle. And in fact, if the circle were only a bit bigger, then you can end up seeing it in your line of vision. So in a way, this is a kind of reference point. So at point x, what you can go from omega 1 and just scale it up to get to omega 2 in a way. If that doesn't make sense, then I'll go ahead and give a bit of other motivation. So suppose that you have a light here. So this could be a light. Sorry for this bad drawing, by the way. And suppose we shine it on an object. Like suppose we have like a stick. Then if we shine this light onto the ground, then we end up getting another stick. So another stick that's even bigger. So whenever we end up shining the stick onto the ground, so let me go ahead and color it. This is the original stick. Then what we end up getting is a shadow that's kind of a magnified version of this original stick. So in a way, we're scaling from this light to go from this to the other. So we're going from the stick to its shadow. So this makes us wonder, can we apply this shining light idea into geometry? Well, as it turns out, we can. And this is precisely the idea of homothety. Okay, so now let's get into the definition. So what exactly is a homothety? Well, suppose we start with a point T. So the point T could be a point like here. Then a homothety is a map from the 2D plane to itself. So we have this entire 2D space here. And we end up going from a point K, and we go all the way to a point K prime on line TK. And this K prime satisfies that TK prime over TK is equal to R. And I forgot to say that R is a real number, which is fixed. And here that means that we are directing the lengths. So as such, that means that R can be negative. So if we have our real number R and we have our starting point T, then this point K goes to this other point K prime, such that TK prime is around R times as far away from T as K. And we're just going in the same direction. So in a way, a homothety is just like scaling up. So let's take a look at an example. So suppose that R equals 2. and this is your point T. And suppose we have our stick again. Then where does this stick go under the homothety? Well, if we start over here, then we go this way, and this is approximately the point where this length over here over this length over here is equal to 2. So this is one point on the stick. And what about this point here? Well, this one goes to, again, we get another point. And we just continue with this with each point on the stick. And then ultimately you end up getting that this is your final stick. So I'm going to go ahead and draw it in a different color. I'll draw it in red. So under the homothety, this is what the stick becomes. So if we take a homothety of scale 2, scale means the value of r, centered at t, this stick here becomes this other red stick here. Now, you might have noticed that these two sticks are parallel to each other, and I'll get to that in a bit. But for now, I want to make you understand an even more important philosophy. So suppose I have a blue ball over here next to the stick. Then where does this blue ball go under the homothety? Well, we can just calculate it out. So then it goes up to over here, I think. Yeah. So the blue ball originally starts off this distance from the stick, and now it becomes over here. And if you take a closer look, you might notice that if we're looking at the perspective of this stick here, the blue ball is somewhere over here, while if we look at the perspective from the red stick, the blue ball is basically in the exact same position relative to it. And this gives rise to another key theorem regarding homothety. And it's probably one of the most important theorems, even though it's very, very self-explanatory. And here it is. So suppose you have any set of points. So let me go ahead and, that's not a set of points. So suppose you have any set of points, and this is a set S of points. And suppose that you have a point T in the plane, and then a point P somewhere here. Then if we take a homothety centered at T, then suppose that this point P is mapped to a point P prime. So we have our homothety H, and we say that H of P equals P prime to say that P gets sent to P prime. And suppose that each of these points in the set get mapped to these other points. So it could be something like this. So over here is the image of under our homothety, and this is the original set. And what we have is that the point P prime here has the same relative position with respect to these points over here as it does with respect to these points over here. So in other words, homothety preserves relative position. This is incredibly strong because in general, if you have transformations of the 2D plane, this is not always true. So homothety is one of these very special ones which just preserves the structure. It doesn't really do much to it other than just scaling up and down. And if you want to prove it, then you just have to convince yourself it's true because things are quite literally just scaled up. And with these homotheties, we end up getting one final thing, and it regards the statement about the stick being parallel to the new stick. And here it is. So suppose you have a point T, and you have a point P, and then a point Q. And suppose that we take a homothety sending P prime here, all the way, and then we take a homothety sending Q to Q prime. So we have that, and we have that. And what we end up getting is that PQ is actually parallel to P prime Q prime. In other words, homothety preserves parallel lines. A homothety sends one line to another line that's parallel to it. All right, so now let's go back to the example presented at the beginning of this video and see what we can do. And this example regards the circles. So suppose we have a circle here and a circle here. And suppose that their external tangents here end up meeting at this point x. Then what do we know about the point x? Well, it definitely seems like we're scaling up from x to get from this circle to the other. And this definitely makes sense given our line of sight and shadow analogy. So that means that when we have these external tangents, then x is the center of homothety. So if we call this omega 1 and omega 2, we can create a homothety h centered at x such that h of omega 1 is equal to omega 2. And because homothety preserves relative position, we can do so much with this. And therefore, let's actually construct the point x with a ruler and compass. So suppose that I cleared this entire diagram. And how do I even know that the point x exists? Like, how do I construct it with a ruler or compass? Or construct it without having to guess where it is? Well, here's where the fact that comes in, where we use the fact that x is the center of homothety. So suppose we have a point P over here, or a point P over here. Where does P get sent to under this homothety, centered at x? Well, this point P ends up getting sent to a point where it maintains the relative position with respect to the circle. So because P has this relative position over here, that means that P ends up getting sent to a point P prime here with the same relative position. And how do we know what relative position means? Well, if we draw in the centers of the circles, then relative position means that these lines are parallel. So that means that given P and P prime, we end up creating the line P prime. And notice that when we take a homothety sending P to P prime, because we're scaling up at point x, this means that this line here actually passes through the point x. So that means that we can take P prime and intersect it with the line through the centers. And it should be somewhere around here. And this is our point x. This is the intersection of the external tangents. And therefore, by taking the tangent here, we have just used homothety to construct the external tangent. In other words, by using the fact that homothety preserves the relative locations of each point, and using the fact that homothety puts one point onto a point on the same line, we end up intersecting those two lines to construct the point x. So this definitely demonstrates the power of homothety and how it can be used to solve some of these really hard problems. Before I get to the examples, I want to discuss a very, very common application of homothety, and it is homothety in triangles. So what is so special about homothety in triangles? Well, as it turns out, triangles have very nice classifications on their homothety. So suppose that you have a triangle ABC, and then another triangle PQ, or suppose that you have a point X in here. suppose I take a homothety centered at X, sending ABC to some other points here. Say, suppose P, Q, and R. Then we know that by homothety properties that these points all pass through a point X. And also from our discussion earlier that PQ is parallel to AB, QR is parallel to BC, and PR is parallel to AC. So in other words, under this homothety, the points A, B, and C get mapped to points P, Q, and R, such that PQ is parallel to AB, BC is parallel to QR, and PR is parallel to AC. And because triangles are so rigid in this sense, it makes us wonder if the reverse is true. That is, suppose that we have triangles ABC, so ABC, and then we have an outside triangle here, and say that is PQR. So suppose this is PQR. Then does it actually hold that these points, that the two triangles have a homothety, that there's a homothety sending one triangle to the other? Because when we have four-sided shapes, this is not true. For example, consider a square and then a rectangle surrounding it. The sides are then parallel, and so are all the angles are equal, but there's not a homothety sending the square to a rectangle because they're not the same shape. But must the triangles be the same shape? As it turns out, this must be the case. So if we can prove that, suppose that these points the lines PA and QB intersect at point X, then we know that there's a homothety centered at X, sending the point A to the point P. So we can say H of A is equal to P, and H of B is equal to Q. And we want to prove that H of C is equal to R. And this basically follows from our homothety preserves point relations theorem from earlier. So basically, because C has the same position with respect to the segment AB as the point R does, that means that X sends C to R. And this means that these points are also collinear. And if you want to be slightly more rigorous with this, then we can use phantom points if you really want to. Specifically, let XC here intersect this line here again at this point R prime. Then we know by homothety that PR prime is parallel to AC, but so is PR. And this forces R equals R prime. So it's just a very quick proof. But the fact that H of C is equal to R just follows from our homothety identification theorem, where the relative positions with respect to points is fixed by homothety. So we can actually phrase this result entirely in terms of something without homothety. So suppose that we have two triangles, ABC, and then PQR out here. So we have ABC and PQR. Then we get that, then because they all meet at the center of homothety, we have that this line here, and this line here are all concurrent. They all meet at the same point, which is the center of homothety. And if I get rid of this point, this is actually incredibly hard to prove without homothety. In other words, we'd have to prove that XC and R are collinear, and we'd have to use the phantom points argument as earlier. And homothety just makes this into one line, which is why it's so powerful. All right, so I want you to keep this in mind as we go through through the exercises and examples. So here's our example, and I want you guys to pay attention very, very closely to this example because it's one of the most important theorems in geometry. So here it is. Let ABC be a triangle with orthocenter H. Prove that all the following 9 points lie on a common circle. So first we have the midpoint of sides BC, CA, and AB. Then we have the feet of the altitudes from ABC to the sides. And finally, the midpoints of AH, BH, and CH. And this circle is called the 9-point circle of the triangle. All right, so go ahead and pause this video and try the problem on your own. When you're done trying the problem, hit the play button and I'll discuss it with you guys. All right, let's solve this problem together. So hopefully you've tried it by now, so hopefully you've constructed a diagram. So I'll construct one now. So let's suppose that we have ABC as our triangle, and suppose that we have our point H here. Prove that the midpoint of side BC, so I'll call that M, N, and P. Then we have the feet of the altitudes, so basically the intersection with the sides. That's D, then that's E, and then that's F. And then the midpoints of AH, BH, and CH. So let's call these, I'll call this X, Y, and Z. We wish to prove that all these 9 points here lie on a common circle. All right, so how can we use homothety on this problem? Or how can we get started on this problem in general? Well, these midpoints of BH, CH, and AH should immediately be a red herring because X, Y, and Z, they all are midpoints. So that means that we can take a homothety centered at H. So H homothety scale 2. Then that means that H of X is equal to A. So H of Y is equal to B. H of Z is equal to C. So the circumcircle of XYZ, where does that get sent to? Well, by the homothety relation theorem that we said earlier, the circumcircle of XYZ has the same relation to XYZ as its image has with ABC. So that means that the circumcircle of XYZ, so circum of XYZ gets sent to the circumcircle of ABC. So that means that we want to end up drawing this big circle in. And if we can prove that all the other 6 points get mapped onto this circle by the homothety, then we are done. So first let's prove that D gets sent to this circle under the homothety. Then this point D prime here is the point such that HD prime is equal to 2HD because the scale is 2. In other words, these two lengths are equal. So we want to prove that the D prime that satisfies this lies on the circumcircle. But I hope this is familiar from the first video or the second video. This is just the reflecting the orthocenter lemma, which I asked you to prove in the exercises of the first video, or I also proved in the second video. And that means that D prime lies on the circumcircle. So do these other points E prime and F prime here. Now all that's left to do is deal with M, N, and P. So we have this other point here, so M, and then we have another point M prime on the circle, such that these two lengths are equal. But again, I hope this problem is familiar from the first video. If we reflect H across the point M, then BHCM prime is a parallelogram. So we can finish the parallelogram like that. And because it's a parallelogram, that means that angle ABM prime is equal to the angle between AB and CH, which is 90 degrees, which means that angle ACM prime is equal to 90 degrees as well. So therefore, M prime lies on the circumcircle, which means that H of M lies on circumcircle. And something similar happens to points N and P. Therefore, the image of every single one of these 9 points lies on the circumcircle. So if we end up reversing our homothety, because the circle gets mapped to a circle by the homothety, that means that all 9 points lie on a circle. And this circle, we can actually describe it even further, is the circle which is the image of the homothety centered at h of scale 1/2 of the circumcircle. So we're scaling the circumcircle down by a factor of 2 centered at h, and this gives us our 9-point circle. All right, so the main thing to get away from this video is that dilation, or homothety, in more technical terms, is much more powerful than you think, especially since it preserves the relation between points, and that makes everything basically unchanged. But it allows us to simplify points that are otherwise very complicated. For example, we could access these points x, y, and z by taking a homothety centered at h of scale 2 and go from A, B to C. And this makes it much easier to handle. All right, so I said enough. Go ahead and try the problems in the exercises portion of the handout. And if you need help on any of the problems, or if you're stuck, go ahead and drop a comment on this video with your progress on the problem, and I'll do my best to guide you on the right track. All right, happy solving, and I'll see you guys in the next video.